Let me start with uh, with explaining some of the key concepts in reinforcement learning, and this would be more like a refresher to these topics, and not I won't be going into like complete depth. So the references for these sections are the OpenAI spinning up blog from Josh Achiam and the RL course from 2015 by David Silver. So the main characters in reinforcement learning are the agent and the environment. So the environment is basically the world that the agent lives in. At every step, the agent can perceive the environment. It resides in a particular state called ST. In this state, it takes an action to interact with the environment from its action set. The environment processes this action and returns like what is the next state for the agent and the reward for this step. And this loop and this cycle keeps happening from an initial start state to a terminal state if the trajectory is finite. So this is basically like a simple agent environment interaction loop. Formally, this same thing can be represented using a Markov decision process. In Markov decision process, you have like the set of states, the set of actions that the agent can take, the transition dynamics, which tells you how states transition from how the agent transitions from one state to another. So it kind of gives us the probability of the next state given like the current state and the action that is taken by the agent. As this process is Markovian, the next state or like basically the future only depends on your current state and action and not the history. R is the reward function. It kind of gives you the expected rewards that you get when you are at a state S and you take an action A. And it's a reward function called RSA. Sometimes these expectations may be written in only in the form of the state or both, say, state and action. So these notations change from place to place. Gamma is a discount factor, and we'll see what is the significance of gamma. So back to the spinning up uh, block. We said that we have like an agent which takes actions. The environment processes that action and gives you, using its transition dynamics, kind of samples the next state and gives a reward to the agent for taking the action. The goal of the agent is basically to learn how to take actions at certain stages in a way that it maximizes these rewards. So we'll define that more formally. So first, let's see what's a state. It's like a description of the state of the world and which where the world you is also including your environment as well as the agent. Not everything in the environment may be available for the agent to view. So sometimes we also say that the environment gives back the instead of the next state like the observation as well. So only the observation is visible to the agent. um, if the observation if the entire state of the agent and the environment is visible to the agent, then it's called like fully observed environment. Otherwise it's called like a partially observed environment. Now, as we defined, like there's each agent has like an can take various set of actions, and the complete set of all possible action is like the action space. The actions may be discrete or continuous, so it actually depends on the agent and environment. The goal of the agent is to learn a policy, and by policy it it means that if an agent is at a particular state, how does it pick its action? So sometimes agents may have like deterministic policies, that is, at any state, it only picks one action, or it may be stochastic. So it can the agent can have like a stochastic policy, that is, have a distribution over the action space given the current state, given a state, and at the time of inference, it kind of samples from this action distribution. So that's is what is referred to the policy. And basically, the goal of the agent is to learn a great policy. Like it needs to learn how to take actions at various states. And how does it do so? We'll come to that. So policies can be, as we said, both deterministic and stochastic. And there can be different ways of designing stochastic or uh, uh, determinate policies. And then there is this action, like the agent environment interaction loop, and that is kind of designated by your trajectory. So basically, the agent starts from an initial state, which is sampled from an initial start state distribution, and at any state, the agent picks its action using its policy. So that the action can, if it's a stochastic policy, the action can be sampled. If it's a deterministic policy, it's a direct function. And at any state st, the policy gives you the action that's picked up by the agent. Uh, Given the action and the state, the environment kind of processes and gives you the next state, some and this can be either deterministic or stochastic. And if stochastic, this is determined by the transition dynamics of the environment or the transition matrix that we saw. So this entire rollout of state action, reward, state action, reward, state action, reward, and so on is called as the trajectory. So in this trajectories, I mentioned rewards. So where does these rewards come from? They come from this reward function, which is like a part of the environment. So it is just, this is nothing but like the expected reward that the environment gives when you are at state st, you take an action at, and you transition to a next state st plus 1. Sometimes this expectation can, in a simplified manner, is written only in the form of the state or in form of both the state and action as stat. So basically the rollout is, you sample initial state from the state distribution, and when you are at any state, you sample an action from your policy, um, and then your transition dynamics of your environment gives you the next state. And based on your state action and next state, the reward function gives you, kind of samples you the reward for that. And the entire rollout of state action reward, from initial state to the terminal state, or if it's a finite trajectory, and otherwise like this entire rollout is called as trajectory. So one important concept is that of return. So return of a trajectory is nothing but the sum of rewards, and sometimes it's also written as the discounted sum of return rewards. Here it's represented by capital R, but often it is represented by G. Um, so G T gives you the return from a time step T. And basically, that is nothing but the total sum of discounted rewards from that time step T. So, what exactly is the RL problem? In RL problem, we basically want to find a policy which maximizes your total expected return. So if you sample trajectories by following your policy, you want to find that policy that maximizes your return. So if you look at just like some of the math, eh, the probability of any trajectory given your policy is can be given by this expression. So it's like the probability of sampling an initial state from star distribution, and then uh, for each time step, like probability of choosing an action at that particular state comes from that policy, and then probability of transitioning from that state to the next state comes from this transition distribution, the transition matrix. That's like the probability of a trajectory given a policy, and the our goal is to maximize this objective, which is like the total expected return uh, from this policy, and that is nothing but if you are summing over all trajectories, we want to take like a mean of that, uh, like the expectation of that return. So it's like the probability of that uh, trajectory times the total return from that trajectory. And the goal is to like find a policy that maximizes your objective, or the expected return, which is like the sum of discounted rewards. So by you can always find, like in for an MDP, an optimal policy, and an optimal policy is the policy which kind of maximizes this objective function.
So now let's look about what are value functions. We have seen um, that we want to measure how good a policy is, and to do that we need to understand the value of a state. So what does the value function mean? The on policy value function v pi of s gives you the expected returns if you are starting from that state and you continue to follow according to your policy. So that is at every you start at that state s, and from there on at every step you take an action that is sampled from your policy. So you start with that state, take an action based on your policy. Once you take that action based on your transition dynamics, you transition to a new state and get some reward from your reward function. Now in that new state you again take that new action based on your policy and keep continuing to do so. So if you collect all that rewards and the return, if you take the expectation of that return, it's what is called as the value function of that. That's like the value of your value function for that state at for that policy. There's another important function called the action value function. So it's represented by q pi of sa. It is also something similar, but it gives you like the expected returns if you start from an state s and an action, and you take an action a, and from there on you continue taking actions based on your policy pi. So the action value function of a particular state and action is the expected returns from that state if you have taken like an arbitrary action a. It's, this action does not necessarily have to be like the be sampled from a policy. It's just the expected return after you have taken this action starting from a state s and then continue to follow your policy. The optimal value function v star of s is basically the value function of a of the optimal policy. Now we mentioned that policies can be compared with each other based on this objective, which gives you like the expected returns, total expected returns when you are starting from an initial state sample from the initial state distribution. So that's how you compare policies. And uh, the optimal policy is basically the policy where your value function is the maximum of all value functions that can be uh, for that state for any policy. So v star s is like the maximum among all policies the expected returns that you can get from starting from that state and following that policy pi. So basically this is nothing but the value function of v pi of s. So max of all v pi of s is nothing but the v star of s, and it can be proved that if you have an optimal policy, it's v pi, like the entire value function at all states is equal to v star s. So the uh, optimal policy is better than any other policy at every state. The final function is the q star sa. So q star sa is nothing but the, again, the, if you take the max of q pi sa among all policies, that's your q star sa, and it is nothing but the action value function of your optimal policy. So let us look at some relationship between the value function and the q value function. So v pi of s is the expected return starting from state s where actions are being sampled from policy pi. It's same as the expected q pi sa, where again, like, the immediate action is being sampled from policy pi, and then since q pi sa itself is the expected return from state s when you take an action a, so that's how this relationship comes about. And v star s, like, is the value function of the optimal policy. Now to think of it, if you are at any state s and you know the q star sa, which is like the total returns, expected returns that you can get from that state if you take an action a, your optimal policy can try to just choose that action uh, which gets you like the uh, maximum value. So v star s is like the optimal, the value function of your optimal policy will be, would kind of maximize if it picks that action which maximizes your q star sa. So hence the value is also equal to the maximum q star sa, and the optimal policy may not, basically you can always find a deterministic policy which is optimal, but there can be a non, um, like a stochastic policy itself, like, as well. But for all the actions that are possible at that state s, that the q star sa for all those um, actions among which its probability has been distributed will all be equal, and will be equal to that of the maximum of all q star sa. So that's like a relationship between v star s and q star sa. Similarly, there are more relationships which we call as Bellman equations. Now, these give you like self-consistency equations for value functions and action value functions. So, say for example, v pi s is the expected return from state s when following a policy pi, can be seen as the expectation of like the immediate uh, return plus gamma times the value function of the next state, where the action here is being sampled from your policy pi, and the next state is being sampled from your transition matrix, which gives you like the probability of transitioning from s to s prime given action a. So probability that st plus 1 is equal to s prime given st is equal to s and a is equal to a. So similarly, there is a similar function for q pi sa. It is the expected of the immediate reward plus gamma times expected value of the q pi s prime a prime, where a prime is being sampled from your policy, and s prime is being sampled from your transition dynamics, and even your immediate immediate action is the same as that given by like the input of q pi sa, and the next action is being sampled from your policy. So that's like the Bellman equation from V pi s and Q pi s a. For optimal value functions, V star s is, as we saw, it's like maximum over all actions Q star sa, and Q star sa. So Q star SA, we can either write it using V star, or again as a along it can be written in terms of Q star again. So V star S is maximum of all actions Q star SA, and Q star SA is immediate like a reward RSA plus gamma times value function V star of the next state S prime, where S prime is being sampled from your transition matrix. Um, and we saw that V star S is like S prime is equal to max overall A prime Q star S prime A prime. So you can replace this with this, and we can get like a relationship of Q star SA in terms of Q star S of next state and uh, all other actions A prime. One final topic is like the advantage functions. So advantage function, we'll see how it will be relevant in various algorithms that we come across. A pi SA, it's like the difference between Q pi SA and V pi S. Q pi SA give you the expected returns when you are at state S and have taken an action A, whereas V pi S gives you like the expected returns from your state S where actions are being sampled from your policy pi. So kind of this difference gives you how good it is to pick an action A as compared to the action sampled from your policy pi. So it kind of gives you a measure of how good it is to pick an action A on average compared to the default behavior of that policy pi at that state S.